Okay, hi everyone, and thanks a lot also from my side to the organizers for the invitation. And I'm kind of new in this field, so even for me, I'm more excited to be here and to learn more about this Koopman Operator Theory. And I would like to specifically thank Stefan as the first person who motivated and inspired me and helped me to work in this area. I'm gonna talk about this work, but I will very briefly mention the main idea of this work. And this paper will hopefully come out soon. And if anyone interested, please just send me an email, and I'm happy to provide more details. Okay, this is the joint work with my postdoc supervisor, Felix Dietrich, and also his students, and with Yanis Keverkidis. Okay, let's get started. First of all, very briefly, I just go to the Koopman Operator Theory. As you know, the main idea of this Koopman Operator Theory is considering the dynamics of observables instead of dynamics of states. And as you can see, this defining equation here, I don't want to go to the details, just it shows how this Koopman Operator Theory ties to the dynamics of the system. Okay, and here very briefly, my take on why this Koopman Operator Theory generally is very interesting. First of all, as you know, each flow has an associated operator, and the family of Koopman operators satisfy the semigroup or a group property. And the second point is kind of pulled under the rug a little bit in many papers nowadays, because actually when we say Koopman operator captures all the information, it's not true to say, but it's actually true to say that Koopman operator theory can capture a lot of information because, for example, for many systems which are chaotic and they have mixed spectrum, then actually this Koopman operator theory doesn't have all the information. And here, as you can see, this spatial isomorphism implies a spectral isomorphism. By this, spatial isomorphism means that we can consider the low-dimensional space of our dynamical system and just define a diffeomorphism. And this diffeomorphism doesn't change the Koopman operator actually, but although eigenfunctions may change by the diffeomorphism, but the spectrum doesn't change. So it means the spatial isomorphism implies the spectral isomorphism, but the inverse is not always doesn't hold. So that is why it's not true to say that all the information, this operator capture all the information. And also the other point is global linearization of the dynamics. Of course, we have this, but just one point, one needs to be careful about this global statements in the context of machine learning, because in the context of machine learning, when we're talking about global, we mean where we have the data, but it's not like the whole plane, just within a small box. Okay, and then as mentioned by almost all the talks, these eigenfunctions are very pretty nice, and they have a large range of applications. And then the other point is that we can estimate this eigenfunction from scattered data when we have some points, and then the other points right after. And also we can approximate error estimate even for finite data. And another point is that it provides us a data-driven design for linear controllers for nonlinear systems. Okay, now the main idea of this work actually is the multiplicative property of Koopman operator eigenfunctions. As you know, of course, products and integer powers of eigenfunctions are also eigenfunctions, as you can see this by definition. And we use this property to generate a large set of eigenfunctions. But how? Well, given we have a small set of eigenfunctions, we can exponentially multiply these eigenfunctions with themselves and with the other eigenfunctions to generate new eigenfunctions. And here specifically is important when technically these eigenfunctions are orthogonal, then it means that the new eigenfunctions are orthogonal again to the previous ones. So it means that it's not just like we have a linear combination of them, which will not be helpful, but we will have a linear span of them. Okay. What are the benefits of having or generating a large set of eigenfunctions? First of all, it can speed up again computation for Koopman metrics. We only need a few eigenvectors, and then we can fill in the rest. And also, we can even obtain eigenfunctions that are not computable with the given Koopman metrics we start with. As you know, of course, with the metrics, we have there is always a finite number of these eigenfunctions, but unlike the Koopman operator, so it's also nice. And the other point, is that the third point is that a larger set of eigenfunctions helps to span observables more accurately, according to this, as you can see. Okay, but there are some challenges for generating this large set of eigenfunctions. First of all, as I mentioned, to start with multiplication, we need a small set of this eigenfunction, but here the question is which algorithm can be used to approximate the first small set of this eigenfunctions. This is very important. And also the other point is that how do eigenfunctions extend across the singularities like steady states, limit cycles, and more complicated ones? I will talk about the second point a little bit more in some examples, but there are still a lot of challenges in this regarding this point. And the third one is that if the system is multi-stable and has a multiple basin of attraction, then what happened for this kind of system? This is also so challenging. Okay, so before going to the method, as you know, we need, as I mentioned also, we need just start with a small set of eigenfunctions, and for that we need to use some algorithm to calculate them, but there are different kind of algorithm, but very briefly. The first one, the original one is DMD algorithm by Peter Schmidt. That was mostly considered for linear PDEs without any reference to Koopman operator theory, but then later it was discovered by Igor. And the other is Laplace averaging through Laplace transform, and also DMD, kernel DMD methods that they use scatter data, and also many others that I don't want to go to the details. Okay. Now here, since we have used this eDMD algorithm specifically to find our results, most of our results, just very briefly, I will go through the idea of that. The idea of this is that just pick the dictionary, whatever, polynomials, neural networks, whatever, then it's very crucial, of course, to pick a proper dictionary, because choosing dictionary poorly, it can result, of course, in a poor approximation. And then if we have some snapshot data like this, you can see, okay, like this, then just we need to evaluate dictionary on this, and then we can approximate a linear map. Okay, well, again, as I mentioned, we will start with a small set of eigenfunctions and then multiply them, exponentiate them. But here it's important to mention that we cannot just exponentially multiply them, and because also on the other hand, errors will also exponentially grow. So what we can do for this we need to define an error function called trajectory error for an extended eigenfunction. What I mean by extended, for example, an eigenfunction of the power of to the power of p, for example, extension in this sense. Okay, we have an extended eigenfunction, an eigenfunction to the power of p, and the associated extended eigenvalue of that. then this error can be defined by this equation, in this term I mean, for discrete time system, and of course for continuous time system by this. And of course here G is a grid that is defined in this way, and also this norm is norm of the on the grid. And we apply this along the whole trajectory to see if this extended eigenfunction is a proper eigenfunction or not. So this is the idea. And also, please note that also there are two main errors in eigenfunction approximation. First of all, the error in eigenvector of the Koopman matrix due to eigensolver, and the other one is that is for both continuous time and discrete time systems, and the other one is the integration error in the flow calculation for just continuous time systems. And it can be written this way, that where this ft is a computed flow, and this one is accurate flow, and we denote the maximum of norm of this all of these errors on the grid by epsilon g. Okay. Now, how we can use these errors to develop some algorithm to exactly find the appropriate, to generate appropriate new eigenfunctions. Okay, here I just very briefly mentioned one algorithm. Of course, we have developed several algorithms, but as I mentioned, I don't want to go to the details, all of them, and the paper will come out soon, and yeah, as I mentioned before, we can provide the details later. So this algorithm, for example, it's a kind of, if we've given an eigenfunction, we can extend, generate extended eigenfunctions in terms of some trajectory error that I showed here. Yeah, this one. And also this error, this maximum of error here, as written of integration error here, this in terms of these two, and some upper bounds. Okay, this is the upper bound. I will go to that. Well, how we can develop this algorithm? Given an epsilon, then to keep this trajectory error below a threshold for a power p, just we need to have this relation, okay? And this is an upper bound for this error. What is it? Just this constants are some constants in terms of the related to the dictionary of EDMD method, for example, for this algorithm, because we use EDMD method. And one considered to the its Jacobian, and the other one maximum norm of all its elements. Okay, and this plot shows it's actually an example of this algorithm, how it works. This is related to a two-dimensional linear system, and if we consider a two-dimensional linear system with two eigenfunctions, we want to exponentiate the eigenfunctions to, and we want to use this algorithm to find the best powers p and q. For example, here for p, here for q for the other eigenfunction. Okay, based on this algorithm, as you can see here, this orange circle shows this upper bound, and this blue circle shows the trajectory error, and this dashed lines shows epsilon, and also this maximum of integration errors. And you can see here, based on this relation, of course, the maximum power to which this eigenfunction can be exponentiated is would be 3, because otherwise the error will be very large, too large. And this is the same for the other eigenfunction. So here you can see how this algorithm can help to specifically find some powers of these eigenfunctions to generate a bigger set of eigenfunctions, and also keep some errors below a threshold, a specific threshold. We can, of course, change it, but then these powers will also change. Okay. And okay, the other algorithms also use this idea, using some are developed based on some errors and some upper bounds. Okay, this was the first thing that I wanted to mention very briefly. And the second thing that we went to it is that we consider constructing eigenfunction across singularity. This is also a challenging problem. And here I show some examples for different kinds of singularity. First of all, the first singularity is steady states. Consider this one-dimensional system with two steady states at A and B, and two eigenfunctions, real-valued eigenfunctions, pk1 and pk2. And it is clear, of course, that these eigenfunctions go to 0 at one of these steady states and go to infinity at the other one. For example, if we consider A in this plots, for example, A equal to 2 and B equal to 3, then as you can see, this one, this pk1, goes to 0 at this steady state and goes to infinity at the other steady state at 3. And the other one also goes to 0 at 3 and goes to infinity at 2. So it is very challenging to construct such eigenfunctions. Because if we have some data just around, for example, here, one steady state, and the eigenfunction goes to infinity toward the other steady state, then the question is, can we approximate values across the singularities? And as you can also see in both plots, these eigenfunctions can be properly defined in the interval between these two steady states, here and here. So we are, of course, it's not still finished, but we can use this, and also the fact that we can convert from one steady state to the other steady state to cross the singularity of the eigenfunction. But I would be happy to discuss this further, and any comments are very welcome, and yeah, very much appreciated, of course. I would like to discuss it later, because this is still a kind of mystery. Okay, and the second example, it's about constructing eigenfunction across the limit cycle singularity. As you can see here, consider the van der Pol equation. This is related to van der Pol equation with a limit cycle, as you can see here in red. And these are isochrones and isostables that have calculated for this limit cycle. And as you know, of course, when we are inside the limit cycle, then we can go to that limit cycle as time goes to infinity, but we cannot escape or cross this limit cycle. So the question is how we can relate the inside and the outside. And yeah, this is another thing, another example. And the last example is constructing eigenfunction across saddle singularity. Okay, as you can see in these plots, for example, here, first of all, these plots are related to a two-dimensional nonlinear system with a saddle at the origin. And as you can see, these eigenfunctions are associated with the unstable direction, and these are associated to the stable direction, and matching with the eigenvalues of the saddle. And the other thing is that we have calculated these eigenfunctions first by considering a two-dimensional linear system with the specified eigenvalues of the saddle. And then for these systems, eigenfunctions are available. Then we used some diffeomorphism, and we transfer the state space, which also transform the eigenfunctions. And then, yeah, we could obtain them. And the other point here is that, as you can see here, this eigenfunctions parameterize the unstable direction, because, for example, if you consider each of these contours, for example, this one, all the points on this curve goes to infinity together, and also reaching the unstable manifold at the same time. And also here, if you consider these eigenfunctions, any point of them goes to the converge to the same point on the unstable manifold. So they are kind of analog to isostables and isochrones. Yeah, again, this is another challenge. Yeah. And just I wanted, as I mentioned, I wanted to bring up these things, specifically the challenges related to eigenfunctions across singularities. And to conclude, first of all, what we did. First of all, Koopman operator eigenfunctions are very important for prediction and presentation of the observables. And two main parts that we did. First of all, we applied the multiplicative property of the operator to generate a large set of eigenfunctions based on some errors using some algorithms. And also for singularities, eigenfunction, as I mentioned, diverge to infinity. We construct a continuation across. But still, as I mentioned, there's some open, some parts are open still. And what are the challenges? First of all, the effect of the noise on the powers of the eigenfunctions is one challenge, and the other thing is large approximation errors in the base eigenfunction. And the last one is continuation across singularities by more challenging, for example, more higher dimensional and so on. And yeah, and by this, I would like to thank you for your attention.